Welcome to this session on work sharing constructs in parallel programming using OpenMP. In this video, we will understand how tasks are divided among threads and how different scheduling techniques improve performance. So before, let us try to understand why we need to understand this high performance computing. Like high performance computing, in short, HPC, is about using clusters of powerful CPUs or GPUs and fast interconnects to solve the problems that are too large for a single machine. That is, knowing the HPC is valuable for the several reasons, like how like solve the complex problem, mainly the real world problems. Like HPC enables the breakthroughs in climate modeling, geomics, or drug discovery, astrophysics, and national security. And these tasks require the massive simulations and the data processing that only parallel systems can handle. And next one reason is the speed and scalability. By distributing the work across the many cores or the nodes, a HPC reduces the runtime from the days to the minutes. Understanding uh, and next one is understanding parallelism, that is OpenMP, MPI, GPU, CUDA, that lets you scale your code data as data problem size grows. And data intensive analytics and AI, that is another reason. Modern AI and ML pipelines depend on high performance computing style resources. So, skills in GPU computing, distributed training, and high throughput data pipelines directly improve model training time and experimentation speed. So the next reason is the cost efficiency. Efficient parallel code uses the resources better. That is a lower compute cost per results in cloud or on-premises clusters. So knowing when to use the batch jobs, queues, and spot instances saves the budget. Next, another reason is optimization mindset. HPC teaches the profiling, memory hierarchy awareness, like a cache, NUMA, non-uniform memory access, vectorization, and the IO optimization skills, so that improve the performance even on everyday applications. So next is an interdisciplinary impact. So engineers, data scientists, and researchers can collaborate across the domains using HPC tools, accelerating the innovation in healthcare, finance, energy, and smart cities, and also the career advancement, like roles in data science, cloud engineering, computational research, and AI increasingly affect familiarity with the parallel computing and distributed systems. In single line, high performance computing HPC knowledge lets you turn big, slow problems into fast, scalable solutions, powering modern science, AI, and industry. So in this video, we will understand how tasks are divided among threads and how different scheduling techniques improve performance. So let us try to understand what is this work sharing constructs in parallel programming, that is OpenMP. So let us understand the basics of work sharing constructs in OpenMP. So parallel programming is a technique where a large problem is divided into smaller tasks that can be executed simultaneously using multiple processors or cores instead of performing operations one after the another, that is in a sequential execution. So parallel programming enables the tasks to run concurrently, which is significantly improves the performance and reduce the execution time. This is especially for computation heavy applications like simulations, data analytics, and scientific computing. So in this context, work sharing constructs, particularly in OpenMP, plays a crucial role. They are special directives that divide and assign the portions of task among threads in a parallel region. So that rather than manually managing the thread workloads, programmers can use the constructs like pragma OMP, that is a for connection for sections, single, etc. So let us see one by one, like for which is splits the loop iterations among the threads, and sections assigns the different code sections or different to the different threads, and single is which is mainly to ensure the task is executed by only one thread. So these uh, constructs helps to ensure that the efficient workload distribution, like a balanced execution across the threads and reduce the idle time, all threads remains active, improves the performance, that is faster completion of tasks. Overall, work sharing constructs simply simplify the parallel programming by automating task division and coordination, allowing the developers to focus more on problem solving rather than thread management. So let us understand little about this OpenMP. So what is OpenMP? And also we'll understand how this what how this work sharing constructs used in this OpenMP for parallel processing. So OpenMP is an application programming interface, that is API, designed to support the multi-threaded parallel programming in languages like C, C++, and Fortran. It allows developers to write the parallel code in a simple and efficient way using compiler directives like pragmas, library routines, and environment variables. Instead of rewriting the entire program for a parallel execution, OpenMP lets you add the directives to existing sequential code. And these directives instruct the compiler to create multiple threads and divide the work among them. For example, uh, by adding pragma like pragma OMP parallel, a block of code can be executed by multiple threads simultaneously. So OpenMP follows a shared memory model where all threads access the same space but execute different parts of the program concurrently. So this makes it easier to develop and debug parallel applications compared to the distributed memory systems. So if you look at the key advantages of OpenMP, mainly easy of use, like minimal code changes are required in order to convert into the parallel, and portability works across the different compilers and platforms. And another one is the scalability, that is utilizes the multi-core processors effectively. So overall, OpenMP simplifies the parallel programming by providing a high-level approach, that is in creating and managing the threads, making it widely used in high-performance computing and also the data-intensive applications. So let us see what are the work sharing constructs. So OpenMP provides several work sharing constructs like for, do, sections, single, and master. Let us see one by one. So this OpenMP, like if you take a for loop, and this for construct is used to distribute iterations of a loop among multiple threads. So each thread executes a portion of the loop, and which improves the performance for the large data sets. For example, if a loop runs 100 iterations and there are 4 threads, each thread may handle 25 iterations. And whereas the second one, the sections, and this is mainly for, whereas this loop is for loop parallelism, that is for loop, and sections next another construct, that is for mainly the task parallelism. So the sections construct allows different threads to execute different independent blocks of code. So each section is assigned to a separate thread. So main uses of this section is when the tasks are distinct. That is a example, like for example, one thread processes the data, another thread writes the output. So we use this single construct, sorry, sections construct. Next one is a singles construct. The singles construct ensures that a particular block of code is executed by only one thread while others wait or skip it. So this is mainly used for operations that should not be repeated, for example, initialization, file reading, etc. Next construct is a master. This master construct allows only the master thread, that is mostly the master thread ID always 0. So that is to execute a block of code. So it is, which is unlike a single, it does not involve a synchronization overhead. That is, other threads do not wait. So overall, these constructs, the open work sharing constructs, divide the work efficiently among the threads, avoid redundant execution, improve the parallel performance, simplify thread management. In short, OpenMP constructs make the parallel programming structured, efficient, and easy to implement. So next one, loop scheduling. In this case, the loop scheduling determines how the loop iterations, like we are going in detail, in a little bit deeper to understand this for loop construct, that is mainly the loop scheduling, how we can schedule it. So this determines mainly how the loop iterations are assigned to the different threads. So that is, choosing the right scheduling improves the performance. So loop scheduling in OpenMP defines how the iterations of a parallel loop are distributed among the threads. So the way this distribution is handled has a direct impact on load balancing, execution time, and overall performance. When a loop is parallelized using the Pragma OMP for construct, OpenMP uses a scheduling strategy to decide which thread execution executes which iterations. Like if the work is not distributed properly, so some threads may finish early and remain idle while others are still busy. So this leads to the poor performance. So common scheduling types, if you look at, uh, there are static scheduling, and this is, and these iterations are divided equally among the threads at the compile time in this case, and it is very low overhead with this, and this is best for the uniform workloads. But it is not ideal if the iterations take the different execution times. And second one is a dynamic scheduling. In this, iterations are assigned to the threads dynamically at runtime. And the advantages, if you look at, like mainly the better load balancing, suitable for the uneven workloads, and it is slightly higher overhead due to the runtime management. So next one is the guided scheduling, and this is similar to the dynamic, but chunk size decreases over the time. So it balances the load efficiently and reduces the overhead compared to the dynamic. So why? Like choosing the right scheduling matters. So here it ensures the balanced workload distribution, minimizes idle time of threads, improves execution speed and resource utilization. So in summary, selecting the appropriate loop scheduling strategy is crucial for achieving the optimal performance in parallel programs. And if you like, if you, yeah, If you could summarize this about like different types of scheduling, and these three scheduling like static, dynamic, and guiding strategies, which helps us to ensure the efficient distribution of work, better CPU utilization, improved overall performance. So choosing the right type depends on whether your workload is uniform or irregular. Like for example, like suppose we have a loop with the 100 iterations and the 4 OMP threads, that the loop is partitioned like 1 to, like suppose the 1000 iterations. If your loop has 1000 iterations, then the 4 OMP threads, and then the first one to 250, and those iterations would be executed by the thread 1, and 250 to 500, and then those that is 250 number of iterations would be executed by second thread, and then 500 to 750 the iterations would be executed by the thread 3, and the last like 750 to 1000 iterations would be executed by thread 4. Okay, so, and if you look at this static scheduling, how we can implement in this OpenMP parallel programming, you can see here the static 2 and the for loop, and there are 10 iterations, and this is going to just to print the ID, that is iterations, and how these iterations are distributed among the threads. And in this case, dynamic scheduling, the threads picks the task dynamically, so it's a better load balancing, a higher overhead. And if you look at the dynamic scheduling task code, in this case you can see this is the way you can you can pass the parameter, the schedule, you can implement this dynamic scheduling. So here the threads dynamically takes the chunks of size 2. Next one is a guided scheduling, and this is the way you can specify this guided scheduling. And this is the way we can mention this, the single constructs. Here you can see here only one thread executes the blocks and the others waits. The single construct mainly ensures that only one thread executes a block while the others wait. And next one is a master construct, And this master construct here, you can see the master construct allows only the master thread to execute without synchronization. And if you compare the master versus single constructs, so here that is in OpenMP, both the single and the master constructs are used to ensure that a piece of code is executed by both one thread, both only executed by only one thread, but they differ in who executes in how synchronization is handled. So if you look at the single construct, that single the directive allows any one thread in the team to execute a block of code. So one thread, other threads wait at an implicit barrier that is by default until the execution is complete. So which ensures the synchronization among the threads. This is mainly useful for the tasks like initialization, I/O operations, or printing, where only the one execution is needed. So any thread can execute, but a synchronization is enforced. That is a key takeaway from this. And next one is a master construct. And if you compare the performance comparisons, like how the static and dynamic and guided scheduling, like how the static, because here the static is fast for the uniform workloads, and whereas the dynamic is handles even tasks like. So when choosing a scheduling status in OpenMP, performance largely depends on how uniform or irregular in the workload is. Suppose if you take the static scheduling, that is a static is a fast for uniform workloads. Work is divided equally among the threads at the beginning. Minimal runtime overhead, that is very fast execution, and best suited when the each iteration takes approximately the same time. And the next one is like a, if it could be the poor choice if workload varies, as it may cause the load imbalance. Next one is a dynamic scheduling, like handles uneven tasks. So work is assigned to the threads on the demand using the execution. So threads request uh, new tasks after completing the previous ones. So this is mainly excellent for the irregular or unpredictable workloads, but slightly slower due to this runtime scheduling overhead. Next one is a guided, and this provides a balance, like it starts with the largest chunks and then reduces the chunk size gradually. So combines the advantages of a static and a dynamic scheduling. This is good for the balance between the low overhead and load balance. This is mainly suitable for the larger scale and partially uneven workloads. So we use the static when work is evenly distributed, and use the dynamic when the work varies significantly, and we use the guided when you need a balanced and optimized approach. So choosing the right strategy ensures a maximum efficiency and better parallel performance. And if you look at the advantages of this, that is work sharing, how it improves the CPU utilization and reduces execution time, simplifies the parallel programming. So this work sharing improves the CPU utilization, reduces execution time, and simplifies the parallel programming. And that can be like how it can be improved. Let us just understand little deep. Like for example, how it improves the CPU utilization. Work sharing ensures that all available threads are actively engaged in executing tasks. Instead of some cores remaining idle, the work is distributed efficiently, leading to the maximum utilization of CPU resources. That is, next one is reduced execution time. That is, by dividing a large task into the smaller parts and executing them simultaneously, the overall processing time is significantly reduced. So this is especially beneficial for the compute intensive applications. Next, easy implementation. That is, simplifies the parallel programming easily. Like work sharing constructs like for sections single allows the developers to parallelize the code with a minimal effort. So there is no need to manually manage the threads, and also the making the code easier to write, understand, and maintain. So work sharing constructs make parallel programs efficient, faster, and easier to implement, which is why they are widely used in high performance computing and data intensive applications. And if you look at the disadvantages, what are the disadvantages with the different types of scheduling constructs? And so in dynamic scheduling, the system assigns tasks to the threads during runtime. So threads repeatedly request new work, which involves extra coordination and the management. So this leads to the higher overhead compared to the static scheduling. So for small or the simple tasks, this overhead can outweigh the benefits of parallelism. Next one is a performance degradation due to the poor choice. Like choosing the wrong scheduling strategy can negatively impact the performance. Like using static for uneven workloads. So some threads finish early while others are overloaded. That is load imbalance. And using the dynamic for uniform workloads, unnecessary overhead reduces efficiency. Next, incorrect chunk size. Too small increases the overhead, too large reduces the load balancing. So increased complexity, like that is OpenMP simplifies the parallel programming, selecting the optimal scheduling strategy mainly requires understanding workloading characteristics, experimentation, tuning, and performance analysis. And then, so while work sharing constructs are powerful, improper scheduling decisions and runtime overhead can reduce the performance. So careful selection and tuning are essential to achieve the best parallel efficiency. And if you look at the applications of work sharing constructs and parallel programming, that is using OpenMP, and this is like used in the scientific computing, machine learning, and big data processing, like weather forecasting and climate modeling, computational physics and chemistry simulations, engineering analysis like a finite element methods. So parallel execution helps process the large numerical computations faster and more accurately. Like suppose if you take a mm, machine learning, parallelism improves the training and data processing, like speeding up the model training, that is especially on large data sets. Parallel feature extraction and pre-processing, optimizing the algorithms like clustering and regression, which enables the faster experimentation and real-time insights. And if you take it a big data analytics like big data processing, here handling the massive data sets requires efficient efficient parallel techniques like data cleaning and transformation, aggregation analytics, real-time data processing pipelines. So work sharing ensures the scalability and efficient resource utilization.